Good evening, and thank you for joining us on Zoom webinar. I'm Eric Walker, Chair of Highlands Astronomical Society, and it's my pleasure to welcome existing club members, new members, visitors from our North of Scotland sister astronomy clubs and groups, and to the first-time visitors who have contacted us wanting to find out what we get up to, and will hopefully consider joining our wee Scottish Astronomy Club soon. We were disappointed after last month's very late cancellation of our guest speaker, so we hope to make it up to you all with a bumper edition tonight. Now, tonight's timings are after my welcome and notices. We're going to have our main talk followed by the question and answer session. At round about 8:30, probably just before, we've got a new feature called Chats. And that's where we're going to show a recorded chat with our own members and find out a wee bit about them and what they've been up to. At about 20 to 9, we've got our club news and Astropics for the month. And then about 9:15, maybe just after, there'll be a wrap up, and that takes us to the meeting close. Now, as usual, there will be a post-meeting Zoom blether. The link will be provided in the chat box, but it should also be in the email you received from Rona notifying you of tonight's events. If it's not in the most recent one, it should certainly be in the first one. As usual, there won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go, but keep yourself connected to the meeting. If you have any questions for the speaker or the club, please put them into the Q&A section at any time throughout the meeting, and we'll make sure they get forwarded onto the question and answerer. Any problems, just click the hand icon and someone will get in touch with you directly via the chat. The chats for general chit chat will be switched off during the main part of the meeting to minimize any distractions, but it will be switched back on near the end. So what have we been getting up to? Well, absolutely masses considering the time of the year. I'm not going to go into any details, or you'll see exactly what we've been getting up to in Pauline's report and presentation. The all-sky camera, it hasn't had much to show, but I notice now the night sky is beginning to get dark-ish in the early hours. Now, if we could only get rid of the clouds. But anyway, back to tonight's meeting. I'm going to introduce our main speaker for tonight, who I'm sure doesn't need much introducing to many of you, Maarten de Vries. Maarten was a long time and very active member with us for many years and played a big part in helping enthusiastic beginner practical observers with observing, navigating the night sky, and getting to grips with using telescopes and eyepieces. I'm one of them, and I'm owe Maarten a debt of gratitude for setting me off in the right direction. Maarten's had a lifelong interest in science. From a very young age, he's been fascinated by the night sky. While not ending up with a career in science, he works for a company that aims to prevent people falling from height, and he's been very actively involved with both HAS and Sigma over the years, as well as with Orkney Science Festival, and I can assure you right at this moment in time, he is well involved with this year's Orkney Science Festival. Besides observing the night sky from his garden in the Black Isle, he's completed several astronomy and theoretical physics courses at the Open University. Maarten's talk tonight has generated considerable interest across our amateur astronomy community, and in addition to our usual enthusiastic members, we have several first-time visitors attending to hear him. I always look forward to Maarten speaking, and his talk tonight is about one of the most numerous stellar objects in our galaxy, which keeps a small army of scientists busy trying to work them out. Without further ado, I welcome Maarten de Vries and his talk for tonight, The Secret Lives of White Dwarfs. Over to you, Maarten.
Well, thank you very much, Eric, for that glowing introduction. It is a pleasure being with you today and delivering the talk. So yeah, I am going to talk about white dwarf stars, and as Eric mentioned, they are extremely numerous. In fact, actually, they could well be the most numerous stellar object in our galaxy. In fact, the whole universe. And I will explain that, of course, later. But amazingly, there is actually not that many people that seem to research these. And also, there is not that much, well, there's plenty of scientific papers written about them. But I actually have had some difficulty finding decent books and information about it. Research in white dwarfs has already taken place for a better part of 120 years. But it is only really quite recently that we are learning a lot more about these quite enigmatic objects. So just a bit about the talk. I'm going to talk a little bit about how they were discovered, because that's quite an interesting subject. Of course, I'm going to explain what they are made of, how they were formed, basically an overview. What we know about them, and also, and I always try to do that in my talks, is to explain how we know this, because yeah, you can rattle off a whole bunch of facts, but it is always interesting to find out how do you work that out. So I will also spend a little bit of time explaining how it is that we know what we know about these interesting objects. I've used a lot of information from this book, which is Unlocking the Secrets of White Dwarfs by Professor Hugh M. van Horn, who is works in the Department of Physics and Astronomy in the University of Rochester. Now, I deliberately put a star rating with this book, because what I'm going to tell you is be aware, if you fancy reading about white dwarfs, this is not an easy book. Clearly, Professor van Horn knows an awful lot about this. He has been involved for a very long time in white dwarf research, but it's a bit unfortunate that he is not a great writer, and I found the book tough to get through. It is very, I find it chaotic, but maybe if you read it, you enjoy it. But there is certainly an awful lot of information there. It is quite up to date. So I did find some real gems in there that I will share with you tonight, but I will also include some stuff that I have learned about from recent scientific papers. And there has been a lot of stuff happening quite recently in terms of white dwarfs, and I will show you what that is. Let's go back then to the beginning, and in fact, whilst William Herschel never knew that he recorded a white dwarf, he did mention that there was he did mention this star here that you can see here on the right hand side. See if I can get my laser pointer going. It should be somewhere here. I, of course, had that perfectly in the wrong spot, so I cannot see where it is. No, I cannot find it. I'll leave it as is, because I don't want to mess this up. Right, so William Herschel did record this Omicron 2 Eridani, and he noticed that besides the fat star there that you can quite easily see, it's quite a decent magnitude. He spotted this other little white star near it, but he had no idea what it was. In fact, it took until 1916 when Ernst Öpik really worked out that this was a companion of what we now know as 40 Eridani b, and that this is a very, very massive star, despite the fact that it is very dim. It's very hot because it's white. So it took quite a while before the true nature of this companion to 40 Eridani A was found. There's also a third companion there, which is a red dwarf, and it is just very dim because it is small and it is not so hot. But this is the first kind of recorded history of a white, what later turns out to be a white dwarf star, 40 Eridani b, and I'll come back to this picture later in my talk. The real star of the show, though, is 1844, when Friedrich Bessel is trying to work out proper motion of stars, of nearby stars, and he started to work on the star Sirius, and that is not so far away, about 8 light years or something like that. So bright star nearby, and he started to work out the motion of this star, and I have drawn the yellow line here on the screen. Indicates the path that Sirius, the star Sirius, follows through the sky. And he noticed quite early on here in 1944 that it didn't go in a straight line, but that it wobbled. And he figured out that the reason for that is that there was an unseen companion in orbit around it that made that path basically swing around the way it does, as you can see here. And but it was quite odd because you couldn't see the companion, or not at the time, but he figured that it had to be very, very massive, the way that it was able to pull Sirius out of its proper motion. And it took about 18 years when in 1862 Alvan Clark, who was a telescope maker, spotted the companion star, and it turned out to be a white star, and it turned out to be very massive. At this moment in time, still no idea what it was, just that it was a very dim star, but very massive. Now in 1917, Adrian van Manen discovered Van Manen star, and this is one of the stars with some of the highest proper motions. This is an artist impression of Van Manen stars because it appears that Van Manen stars has planets in orbit. So in 1922, Willem Luiten basically worked out that this was again one of those really hot, very low luminosity, super dense or very massive stars. So they must be small, because if they don't send out a lot of light, they must be small. And it was actually Willem Luiten that coined the phrase white dwarf, or about that time the phrase white dwarf for these stars was coined. And also around that time, people started to work out what these objects really were. That they were so massive and that there were obviously a few around was interesting enough, but what were they made of, and what were they doing, these white dwarfs? So to recap, these white dwarf stars are small. They are, in terms of their size, about the scale of the Earth, but they are very hot, and they are extremely massive. That is to say, they are anywhere between about half to just over the mass of our entire sun. So whilst the sun is absolutely humongous, as you can see in this slide, white dwarfs are very small, but they are not necessarily that much lighter. And that obviously means that these white dwarfs must be made of something really kind of truly amazing. In the beginning of the 20th century, we started to understand things like quantum physics and quantum mechanics, and were able to start to make some guesses what was going on with these white dwarf stars. So from observations alone, by looking at their proper motion, by looking at how they tug on other objects near them, like companion stars, we know that they are around 0.2 to 1.3 times the mass of the sun. So in the order of the mass of the sun. They're extremely hot. The fact that they are white and sometimes even blue-white, they emit a black body spectrum the same way as our sun does. And from that, we can figure that they range around 6,000 to 200,000 Kelvin, the surface temperature of these objects. And most of them are way hotter than 6,000 Kelvin. 6,000 Kelvin is just about the temperature of the surface of our sun, slightly lower than that. So we have a very high surface brightness because of their heat, but because they are very small in diameter, they don't radiate that much light, and therefore the absolute magnitude is quite small. They are around the same size of the Earth, which means, in the order of 2 pro mile to about 20% of the radius of the sun. What is most peculiar and hinted on what was going on inside the star is that the more massive they are, the smaller they are. And that is, of course, very odd, because normal stars, main sequence stars, the more massive they are, the bigger they are. But that's not the case with white dwarfs. In fact, the most massive white dwarfs that we know, the ones that are around 1.3 times the mass of the Earth, are only slightly bigger than the moon. So there is actually really something curious going on. And of course, because they are so small and because there is so much mass, they must be extremely dense. And we are talking here about, and I say 1,000 kilograms, that's wrong. It is 1,000 tons per cubic centimeter. That is an error here. It's 1,000 tons of matter per cubic centimeter. So this is exceptionally heavy. They have a very different spectrum from normal main sequence stars. So when they were able to start to obtain spectra from these stars, they spotted a number of things. For starters, that the spectrum is redshifted. And that is obvious as a result of the very, very high gravitational pull that these very massive stars have. In fact, actually, if you would stand if you were able to stand on a white dwarf, you weigh in the order of 50,000 kilograms. So the pull is very, very, very strong. And it is also interesting to see that the spectra are very peculiar in the sense that there is very often only one particular element available in the spectrum, and nothing else, or very little of anything else. And that's also giving a clue of what is going on. So that is what we can see by observation, by using telescopes, by measuring their motion in the sky, and by doing things like spectroscopy to work out their temperatures and so on. Now, I think that quite a few of you recognize this Hertzsprung-Russell diagram, or HR diagram. This is a way of plotting stars in the night sky on a chart where we can compare their luminosity with their surface temperature. And if you do that, then if you look at loads and loads and loads of stars in the sky and you plot them on this graph, then you get this shape. And what you find is that most of the stars sit in this band here, and that tells us that cooler stars tend to be smaller and less bright, and hotter stars tend to be brighter and bigger as a result. There are some giants and supergiants here. They are basically cooler but very big stars, and as a result they are bright as a result, because the bigger the star, the brighter they get. It's just more surface area for light to escape the star. And then we also have down here our white dwarfs. So these are the stars. They tend to be quite hot, as you can see. They are almost as hot as the hottest so-called main sequence stars, but they are a lot dimmer. So they live here. So what are they doing there? How did they get there? What's happening? Now, we now know that white dwarfs, through all the studies that we've done and all the observations and work that we've done, that white dwarf stars are in fact the end product of main sequence stars. So a main sequence star goes through its life, and depending where this star lives on this main sequence, sooner or later, they will go through a period where they will expand into giants or supergiants, depending where you are in this on this chart. And then after that, some of these stars, and I'll explain which ones, but mostly anything under 10 times the solar mass, once they have become a giant, they will then drop down and become white dwarfs. Now, why don't we see any stars between these? That is because the period it takes to go from main sequence star to giants, red giant status, and from red giant back into white dwarf, they are very short. These periods are quick. We are talking about millions of years rather than billions of years, and sometimes only hundreds of thousands of years or even less for a red giant to turn into a white dwarf in the end. But that's what's happening. So stars that are living their life mostly on the main sequence eventually become red giants, and then they once the outer envelopes of the star has disappeared entirely, all that is left is the hot dense core of the original star, and those are the white dwarf stars. Now, before I'm going to explain a bit more about how they actually form and what they are made of, I need to tell a little bit about degenerate matter, because I'm going to mention this a few times, and that it plays massive roles in white dwarfs. So what is degenerate matter? Well, it's a theoretical state of matter at zero temperature, and therefore, when you read a book like Hugh van Horn's Unlocking the Secrets of White Dwarfs, they're talking about zero temperature or zero Kelvin white dwarfs. Now, that makes absolutely no sense. And it makes no sense because these things are extremely hot. So why are you talking about 0 Kelvin? And that is because there is an equivalence. The matter that these stars are made of is similar to the matter that exists at 0 Kelvin. Now, you know that it is not possible to reach 0 Kelvin, or I hope you do know that it's not possible to reach 0 Kelvin, but you can also make matter degenerate by really, really compressing it a lot. And I'm talking a lot more than what happens in the core of our sun. What happens is if you compress matter a lot, then at some point the Pauli exclusion principle starts to enact. And what that does is it stops fermions, and fermions are things like electrons, protons, and neutrons, to get any closer to each other. Now, electrons repel each other already through the electromagnetic force because they are negatively charged, and two negatively charged electrons expel each other, but we're not talking about that. That is actually, well, not easily overcome, but once that is overcome, then we have the situation where these fermions don't like to sit in the same space. Things like photons, they are bosons, they can live at the same place. They can actually fly through each other and never notice each other, but you can't do that with electrons. Now, it's interesting because lighter particles need more room than more massive particles, and that is to do with the fact that particles obviously, or not obviously, but for those that don't know, particles in the very, very, very small sense in the quantum world behave wave-like, and their wavelength, their associated wavelength, depends on their mass. And you find that the less massive a particle is, the larger their wavelength is, and the more room they need, because these particles need to live in a space where they can basically produce their full wavelength. You cannot have a particle in a place where it can only have a part of a wavelength. The particle won't tolerate that. Something has to happen. So electrons, because they are a lot less massive than, for instance, protons and neutrons, need more space than protons and neutrons. And that's why, for example, also in an atom, you find that the core, where the protons and the neutrons live, is very, very small compared to the cloud of electrons that is around them. That's because electrons need a lot more room. Now, the fact that that these electrons don't want to live in the same space creates a pressure. It creates a resistance of pushing these electrons even further close than they already are. And this is exactly the same as in an atom. An atom is also a space where electrons are really, really densely packed around the core of the atom, and they can only occupy certain so-called quantum states. And in degenerate matter, basically, this becomes true for the whole volume. So instead of just looking at an individual atom, you now need to look at all atoms. In fact, the atoms are no more. The cores of the atoms are just basically all together, and so are all the electrons. And it is the electrons that stop all the matter from being crunched further together, because they cannot all live in the same quantum state. And some people say, oh yeah, but you can eventually overcome that. And the answer is actually, no, you can't. The only way that you can further compress degenerate matter is by removing the electrons. And that is exactly what happens in really massive stars. Anything more than 10 solar masses, if that in the end of its life starts to contract, then what you get this situation is where the electrons are interacting with the protons to form neutrons and neutrinos, and the electrons are gone. And now there is no longer electrons in the way to make the star further collapse, and then you get a neutron star, or even, and if that collapses, then everything collapses into a black hole. But the first phase of resistance that you get when you really compress matter together is this so-called electron degeneracy. Now, here's a couple more interesting bits that we need to remember. Ordinary matter, and especially gas, like what our sun is made of, we can apply what is known as the ideal gas law. And that means that when you multiply the pressure with the volume, then this is proportional to the temperature. What that means is that if I compress it more, the temperature goes up. Or if I increase the temperature, the volume needs to increase. And that is why it's possible for the sun to live, because it won't collapse. Because if it collapses, the pressure goes up, the temperature goes up, we get more fusion reactions happening in the sun. That increases the temperature even more, and that halts the further collapse because the volume wants to increase, the pressure wants to increase again. So in an ideal gas, these three things, pressure, volume, and temperature, are in balance with each other. Not so in degenerate matter. In degenerate matter, pressure times volume is not proportional to temperature at all. So you can increase the temperature of degenerate matter till the cows come home, nothing will happen. The pressure stays the same, the volume stays the same. The only thing that you can do, the only thing that can increase the volume is the amount of matter that you add and increase the gravity of the whole, the gravitational pull, the whole mass of it. Another thing that a lot of people don't realize, and that was something that I actually also learned and had to get my head around. In degenerate matter, the electrons are completely free to move about. You think, hey, if they are so close together that they cannot, that they are resisting being pushed closer together, surely they must somehow become concrete, they cannot move around. No, they can, and they can quite simply for again, quantum physical reasons. They can exchange position quite easily, and that happens. They move about. In fact, the Heisenberg uncertainty principle plays a major role in this too. But what you find is that the electrons in degenerate matter move around really easily. In fact, degenerate matter is very much like a metal in that case. So it is an effective conductor both of electricity and also of heat, because it is the electrons that move the heat about in degenerative matter. So now we know enough about degenerative matter. Let's talk about stars again. So this is an ordinary star, say our sun. It's made out of a ball of very hot hydrogen, and in the center of it, the temperature and the pressure is so high that the hydrogen is fused into helium using the proton-proton process, as we call it. So two hydrogen atoms, nuclei, are fused into a helium nucleus. Now, that happens for a while until more and more helium builds up in the core of the star. Then what? That's the question. Now, that depends entirely on the mass of the star. So let's first look at our first series of stars, and those are stars that are slightly less massive than the sun, say about 80% to about 200% the mass of our sun. Now, in that case, the helium that is formed in the core is not hot enough or not hot and dense enough to go and fuse itself into heavier elements. It remains helium, and if enough builds up, it will then shrink and become degenerate because there is no fusion taking place inside the helium. It cannot, there is no hydrostatic equilibrium, as we call it, so it is not possible for the extra heat to be produced to keep the helium from collapsing under its own weight, and it will start to shrink under its own weight and becomes degenerate matter, as I explained earlier. At some point, the pressure, however, becomes so high that the helium nuclei are getting close enough to fuse. Because it's not only the temperature, but also, if you push them close enough, eventually some of them will stick together and fuse, and that will produce heat. Now, as I said earlier, degenerate matter, if you increase the temperature, nothing happens. It is not expanding. So that heat that is produced by this fusion reaction in the degenerate matter doesn't do anything. It doesn't then expand the matter and stops it from fusing like it would do normally in the sun. And the resulting rise in temperature quickly, processes through the whole core, through the whole degenerate core in a runaway fusion reaction. The whole helium core then fuses to carbon and oxygen in a matter of seconds, and we call this a helium flash. And this is exactly what is going to happen with our sun, because that is a star between 0.8 and 2 solar masses. Don't worry, it's not going to happen for another 5 billion or so years, but our sun will eventually have this helium flash happening at its core. Now, interestingly, this helium flash will not explode in such a violent explosion that it will disrupt the star. It will bloat. It will become big and red and huge, but it will survive this helium flash. Once the helium has flashed into carbon and oxygen, the carbon and oxygen will itself start to contract and become degenerate. So now we end up basically with a carbon-oxygen degenerate core. Now, the heat on the outside of the star will eventually, on the outer regions of the star will eventually, the radiation that is created by it will eventually blow the outer layers of the star away. Also, this ring of hydrogen burning will get closer and closer to the edge, and eventually there is not enough mass to hold that fusion reaction back, and these outer layers of the star will basically blow into space, exposing most of that carbon-oxygen core. And that carbon-oxygen core will then form the white dwarf star. Now let's look at some other star masses, because we said, of course, this was 80% to about 200% of the solar mass. What of stars that are bigger than that? Well, the helium in that case will start fusing into carbon and oxygen before it can become degenerate. So you will not have a helium flash, but it will just basically quietly, if you wish, fuse into degenerate carbon and oxygen. The same thing will happen on the outside of the star. The hydrogen burning will be in a shell, and it will more and more get to the outside and eventually blow the outer atmosphere of the star. But we won't see a helium flash. Anything bigger than that, anything about 8 to 10 times the solar mass, the carbon and oxygen itself will start to fuse. It won't become degenerate, but it will start to fuse. And produce things like neon. However, beyond neon, in stars of those kind of masses, it won't be able to produce any further fusion reactions, and again it starts to become degenerate, and we end up with an degenerate oxygen neon core. But the same thing applies when you now have a white dwarf eventually that contains a degenerate oxygen neon core. Anything bigger than around 10 solar masses will eventually, the matter, the core will eventually exceed the so-called Chandrasekhar's limit of 1.44 times the mass of the sun. So the core will exceed the mass, not the star. And when that happens, that is the moment in time where the electrons are no longer able to hold back. They will then interact with the protons and create neutrons and neutrinos and become a neutron star, or worse still, if the star is even more massive, it will completely collapse into a black hole. And this will happen in a big giant type 2 supernova. That's a talk for another time. What about stars of less than 80% of the solar mass? Well, that's an interesting question. Our galaxy is not old enough for such stars to have formed, because the thing is stars of less than 80% of our solar mass will eventually be much older than the nearly 14 billion years that the whole universe is old. So those stars haven't reached the end of their lives yet. So in theory, well, in practice, there are no white dwarfs formed from those stars yet. We can theorize. In fact, actually, we know for sure that any star that is half the size of the solar mass will not do anything after the helium core is formed. The helium core will not be dense enough to create a helium flash and therefore remain helium core. But we don't have, they are theoretical. There are no helium core white dwarfs around because our galaxy, our universe is not old enough for those. Now here I was talking about these gas layers being blown off at the end of the life of the star. I didn't want to go into too much detail there. And that would be for another talk to talk. I've talked before about planetary nebula and what's happening there. But it is suffice to know that at the end of the life of a star, when things are starting to go haywire in the core, and the hydrogen is starting to burn in shells away from the core, that pressure that is generated will eventually take the outer layers of the star and blow them off into space. Either, well, mostly due to thermal radiation. And when that happens, you get these incredible things like these planetary nebula. And this one, of course, super famous, M57, the Ring Nebula. Despite it being, over 2,000 light years away, it's a wonderful object in even a small telescope, and you can clearly see the ring structure. It's a big thing. But look at the age. It's only 7,000 years old, they guess, which is quite remarkable. So this last phase of the star is really quick. And in a few thousand years, this nebula will have spread out so much that it starts to become fainter and fainter until we eventually won't be able to see it. But right at the center of this, we see the carbon-oxygen core of of the original star, and it is shining very, very, very hot. In fact, actually, this thing is around 200,000 degrees on the surface, and that's the reason why this whole nebula, a size of 1.3 light years, is glowing, because of the enormous amount of X-rays and ultraviolet light that is being shown from this proto white dwarf. It's known as a planetary nebula nucleus at this moment in time, but it is in fact a very, very young white dwarf, still with its cocoon around it. So here are a few possible white dwarfs. So I mentioned that most of the white dwarfs that we know have a carbon-oxygen degenerate core. Some of them, the biggest stars, but they are rarer, the 8 to 10 solar mass star, they have oxygen and neon cores. What you will find that very often these oxygen and neon white dwarfs have very little envelope around them. They have hardly anything else but oxygen and neon degenerate core. The other two kinds, they have what they call these envelopes. Now, I have not drawn them to scale here. They are really very minuscule. The atmosphere around these degenerate cores are very small indeed. We are talking, maybe 50 kilometers or so. We are talking about 0.4% of the mass of the sun in either helium or hydrogen. So there's very little left. Very often this hydrogen and helium is basically something that has fallen back out of the planetary nebula, or for other reasons remains there. There are various theories about why these envelopes are there. But what is quite significant is that they are segregated. They are extremely segregated, and that is because helium is about 4 times as heavy than hydrogen, and because the density and the gravitational force is so high that the helium basically precipitates out of the hydrogen and sinks to the bottom, if you wish, on top of the carbon and the oxygen. And that is why when we see a star like this, all we see are hydrogen spectral lines and nothing else. And in the case that the hydrogen is completely blown out in space, all we see is helium spectral lines and nothing else. Sometimes we do see a little bit of carbon inside the helium. And that can happen when at a certain stage during the cooling process of these white dwarfs, because there's no fusion going on in these. So they cool down very, very slowly over very, very long period of time. We are talking about trillions of years. And during that cooling down period, at some point when they reach certain temperatures, you will start to get some convection taking place inside these envelopes. And it can at times, they have worked out theoretically and now proven by looking at the spectra, dredge up some of that carbon from underneath. Very often the carbon and oxygen are also not mixed. The oxygen being heavier than carbon sinks to the center of the star eventually. And as we shall see later on, it was already mused in the 60s that when the stars cool enough, that oxygen eventually starts to crystallize out and snow fall as kind of oxygen snow at super high temperature still, though, to the center of the core of the star, and eventually all the oxygen will have precipitated out into some kind of crystal, oxygen crystal, and then the carbon starts to crystallize out, and eventually the whole carbon oxygen core will be crystallized. It will be a solid forming a oxygen crystal with a carbon crystal around it. And sorry for those nuts that hope that those carbon crystals are diamond. No, they're not. It's a completely different type of crystalline structure that this carbon forms. And it will also be still very hot and very far away. So unfortunately, we cannot make any riches yet from this. Now, these different compositions of white dwarfs give rise to different spectral classes, and the spectral classes that they've come up with all start with D for degenerate, and then we have basically A, B, C, O, Q, and Z. And A means hydrogen only, and these Balmer lines are quite wide, and they are wide because of the very, very high gravitational attraction. The DB class, we see mostly hydrogen 1 lines in the spectrum. So that tells us that there is almost pure hydrogen envelope around the degenerate core. And in DC, we see a continuous spectrum with hardly any lines deeper than 5%. And why that is, possibly because there is very little, it's maybe only a couple 100 meters thick, the helium or hydrogen that is still present. But possibly also because it is being churned up a lot because of convection. And then we have the DO. There are helium-2 lines, and some helium-1 and H lines may also be present. And again, the mixing that is taking place here, very likely due to convection inside the what they call the envelope, the gaseous envelope around the core. Now, the DQ is where I mentioned the carbon features, either atomic or molecular, and that can be in any spectrum. That could be in a hydrogen spectrum or a helium spectrum. If you see some carbon, that is a sign that something is going on, and there could be 2 reasons for it. I already mentioned convection, where basically the movements in the gas eventually dredge up some of that carbon from the degenerate core. But it can also be because of mergers, as we have now recently seen in a paper that was written about this subject, where 2 smaller white dwarfs are in orbit around each other, and this orbit degenerates because of relativistic forces, and eventually these two white dwarfs merge. And when that happens, obviously a lot of churning goes on, and a lot of carbon is mixed with the envelope, and then we see these carbon features. And finally, you may also see some metal lines, but only metal lines. And what we mean is anything heavier than helium or hydrogen is called a metal by astronomers. Yeah, don't ask them, But anyway, if there are no helium or hydrogen lines and only metal lines, then we're talking about a DZ, and these DZ stars are very rare. The most common ones are DA and DB, as you shall see, and DA probably the most common of those. Now, how did we work this all out? Well, that was a lot of work, because once we started to understand in the early 20th century that that these stars, that some kind of what you call it, quantum mechanics took place in these stars, we then needed to start to model this. And what they did is they just basically took a sphere of a certain diameter and a certain density gradient, and they basically divvied it up in about 100 shells. So rather than calculating the whole sphere, which you cannot do, what we'll do is we calculate every shell and take into account the shell above it and the shell below it. So like an onion, if you wish. And they basically worked out the formula to calculate the pressure, the temperature, and all that stuff for that one shell. And then do the same thing again for the shell underneath it, and the shell underneath, and underneath, and underneath that. Taking into account the pressure created and the temperature and whatever it is, the opacity for radiation to be able to escape, all that stuff, taking that all into account, they were able to calculate this by hand. It was an enormous amount of work. They actually had small armies of people, they called calculators, which was, I have shame to say, very often women. They are very good at it, obviously, but that was just what was the case in the earlier part of the 20th century, doing all these calculations for astronomers to work this out. And yeah, what by doing the calculations and applying physics, by applying quantum physics, by applying gas laws, by doing all this stuff, you can actually work really out a theoretical white dwarf. You can work out where the matter is degenerative, where it is not. You can work out where stuff is gradually changing and where it abruptly changes, and it could work all these things out. And amazingly, even then, when they were using this kind of crude method, although very diligently, they were able to create models, theoretical models, that very, very closely resembled what they could see through the telescope and in their spectroscope. So that corroborated their observations with the theory. But then in the late 40s, early 50s, actually mid 50s, perhaps more commonly, we started to see the introduction of computers. And funnily enough, actually, white dwarf calculations lent themselves so good to computing, and all kind of calculations like that. That certainly the white dwarf science world really latched on very quickly to electronic computing to go and start to do these calculations. And not only could they do these calculations, of course, much faster, but they could also do more calculations. They could now take the star and divvy it up in more than 100 layers and go to maybe 1,000 layers to get far more precise results. And they can do it much more quickly, and they can change the parameters more often to see what would happen. And that resulted in even better and more precise models of the stars that even better corroborated the stuff they could see happening in the actual sky. But I think the biggest breakthrough, and in recent years, because we were talking about the start of the 20th century, we knew about 3 white dwarfs. By the end of the 20th century, we knew about a few thousand. Now we know about 200,000 or so or more white dwarfs. And why is that? Now, it's thanks to this particular space probe here, Gaia, which was launched in 2013 and expects to operate until next year, hopefully a bit longer, because it's a fantastic piece of equipment. It's designed for astrometry, and that means measuring the positions, distances, and motions of the stars. And it can do that exceptionally precise. And with that, of course, they can measure, especially of multiple star systems, the orbital velocities of the stars, and thereby working out exactly what the masses of these stars. And as a result, Gaia has now discovered well over 200,000 white dwarfs. And when you do that, when you have so many of these white dwarfs, you can then start to do some interesting statistical analysis on them. And here is basically a HR diagram again, but only of the white dwarfs. And when you look carefully, you can see that there are some layers in it. When you have enough white dwarfs, you can start to see this. If you don't have enough white dwarfs, you don't see this. But with enough white dwarfs on this diagram, you start to see that there's layers in it. And this layer here is of particular interest. This one here, you can see there is more stars here than there is there, and there is more stars here in this band than there is before and after it. And this means that when the stars cool down, because the cooling down goes in this direction, that when the stars cool down, that cooling down slows down and then speeds up again. Hey, that's interesting. So they cool down very, very, very slowly, and then they stop cooling down. They start to bunch up. And this completely agrees with the crystallization of the core of these white dwarfs. So Gaia has, by discovering all these white dwarfs and putting them on this graph, now proven that this crystallization indeed takes place inside these cores. Why does it slow down? Well, the same way as when ice, when you freeze something, the temperature goes down and down and down till it reaches 0 degrees centigrade, and then the ice starts to freeze. And while the ice is freezing, it doesn't get colder. And it's called latent heat. And we see that in these cores. So the latent heat stops basically these cores from cooling down quicker. Interestingly, I need to say, and I forgot earlier, but these stars are very good at moving heat around in their core. The core is actually pretty much the same temperature everywhere, and that is because remember these electrons, they can move about so easily. You know, the heat can be spread very easily throughout the star. So when the core starts to crystallize, you know, that latent heat can just basically very easily escape to the edge of the star, to the surface of the star, and radiate out into space. So this picture shows us that this crystallizing takes place. And as I say, it is again, by making those models using computers, but by looking at the observation, it is clear that what happens is that the oxygen crystallizes first. It sinks to the bottom, if you wish, because it's heavier than carbon, and then eventually the carbon will also crystallize until the whole core is basically crystallized. And that we can see that that's happening. Now, interestingly, we can see that in heavier white dwarfs, that crystallization takes place at a higher temperature than for lower mass. See that these are lower mass white dwarfs, these are higher mass white dwarfs here. And the higher mass white dwarfs, they crystallize first. And that makes a lot of sense, because those higher mass white dwarfs, they are denser, and it is not just a matter of cooling, but it is also a matter of pressure. So it is at a certain temperature, at a certain pressure, the crystallization starts, and therefore you will find that in high mass white dwarfs, the crystallization starts much earlier than in low mass white dwarfs. And here is also interesting, where you can see that high mass white dwarfs are less bright than low mass white dwarfs. And now the question is why? Well, remember what I said, high mass white dwarfs are smaller. The more massive they are, the smaller they are. Therefore, they have less of a surface area from which they can radiate heat, and therefore you will find that they are basically less bright, and therefore also take much longer to cool. And you can see that in the graphs here. The red dwarfs, the low mass white dwarfs will eventually run out of steam earlier. That is this bend here, than the more massive ones. They will remain hotter much longer, because the area from which they can radiate the heat away is much smaller. And there is of course also much mass that can retain the heat. Now, I've already talked briefly, and I need to keep an eye on the time now, about white dwarfs that were spinning around each other, and they do. But you can also have a situation where you have a white dwarf with a normal main sequence star, and when that main sequence star comes to the end of its life and it starts to bloat, then there will come a point where that bloating star, if they're close enough, that goes past what we call the Lagrangian point number 2. And when that happens, then the mass will start to be pulled into the white dwarf. So the white dwarf can accrete additional material. And if you have two white dwarfs and they plunge into each other eventually due to gravitational, relativistic effects, then they too can reach a point where the mass of these stars are going to exceed the maximum. And we are talking about exceeding Chandrasekhar's limit. Now, the thing is I need to say is that never happens. It will never reach the point where they suddenly collapse into a neutron star, because something else happens. Carbon and oxygen degenerate matter, when it is about 95 to 98% as massive as 1.44 times the mass of the sun, i.e. Chandrasekhar's limit, then we also get a runaway fusion effect. The carbon and oxygen start to fuse suddenly. And that goes a lot wilder, a lot more, explosive than helium runaway fusion. In fact, it is so powerful, this carbon and oxygen runaway fusion effect, that the whole white dwarf blows to smithereens in a almighty type 1a supernova. And here is one of those supernovas. This is the supernova in 1994 in NGC D in NGC 4526, and you can see it outshines the entire galaxy. This as bright, or if not brighter, than the core. And this is a different type of supernova than massive stars collapsing. Type 1a supernovas are white dwarfs that for some reason accrete too much matter from either a nearby star or by mergers of two white dwarfs, that they exceed this limit, and you get this carbon oxygen, flash you could call it, but it is an almighty explosion. Now, nothing is left after it. The type 1a supernova doesn't leave neutron stars or black holes. It just blows everything, blows into smithereens. And it is in fact, there is now studies showing that these type 1a supernovas are largely responsible for the high percentages of carbon and oxygen in our universe, because that is how that oxygen and carbon gets flung out into the universe, into the interstellar space, and then can form with other dust, can form back into other stars that can then produce planets and so on that contain that carbon and oxygen. There's another really interesting thing, because these white dwarfs almost always start to explode exactly at the same mass. These supernovae are almost exactly the same brightness. And that is interesting, because that means that if you know the brightness of one of these supernovae, 1a, by looking at another type 1a supernova, you can work out the distance. And it is exactly that which was used to find that our universe is expanding faster than we thought it was. Because the further away the supernova are, the more redshifted they are, more redshifted than we expected them to be. So it turns out that the universe is expanding, the expansion is accelerating, and it was possible using these type 1a supernovae to work that out. So when a white dwarf reaches 99% of Chandrasekhar's limit, carbon starts to fuse. Heat does not expand the core, as we know, because it's degenerate. We get again a runaway fusion reaction. Most of the carbon and a significant amount of the oxygen fuses within seconds. The entire white dwarf rips apart. Nothing is left but an expanding cloud of gas. And this is a type 1a supernova. And all of them have a very, very similar brightness profile. Here are some examples of supermassive white dwarfs that are very close to this. They're not that far away. We're talking 130 light years. If something like this one here would go boom, we would certainly see it here. It would be extremely bright. Whether or not they will, that depends entirely, whether or not there is enough, whether or not they will be able to accrete enough gas. And as far as I know, these, do not have any companions. What is the case, though, is that this particular one is spinning very fast. This seems to be a merger of two white dwarfs, and as a result, it spins very fast. And that is a good thing, because a very fast spinning white dwarf is much less likely to go supernova than one that isn't, and that is because, of course, the spinning will create a centripetal force that reduces the pressure inside the dwarf. Now, these spinning white dwarfs spinning around each other, we will hopefully soon, and I say soon, in 14 years' time, be able to see these using this follow-up from LIGO. This is the LISA concept. It is basically the same as the LIGO gravitational wave detector or detectors that we have, but this one is just a bit bigger. Instead of a few kilometers long arms, this one have 2.5 million kilometer long arms. So there's 3 of these spacecraft, and they basically form this L shape through these laser beams, and that will be launched in 2034. And then after that, we will be able to see these mergers of white dwarfs happen, and that would be really interesting. Now, to finish up, I'm going to talk a little bit about 2 more things. One is, it turns out that you can have variable white dwarfs, and in the 60s this had been discovered. They don't vary a lot, and they vary in a very, very interesting way. The variations are quick, as you can see, tens to thousands of seconds. It's not over days, and there seems to be, like in mainstream stars, or main sequence stars, there seems to be some form of an instability strip, a place within the HR diagram where these stars start to exhibit these variations. However, it's unlike, like for instance, RR Lyrae variables or similar Cepheid variable stars. It's rarely that the whole star pulses in and out. It's more likely a very complex oscillation that takes place, a little bit like what would happen in an earthquake. It's thought mostly that these variations are caused in changes in the ionization of carbon in the outer layer, because what happens is if carbon ionizes, then the electrons will make the whole gas opaque, and then any heat from inside it will not be able to get out. It will raise the temperature of the carbon outer layer. That will then swell a little bit up until it cools down enough for the ionization to stop. It becomes transparent again, the light can flash out, and therefore it shrinks back in. So that is one reason it could happen. There could also be some acoustic reasons for it, especially where maybe you have a degenerate core that spins faster than the envelope, the gas envelope around it, things like that. Can also be a result of very strong magnetic fields. There are super strong magnetic fields associated with some white dwarfs. Now, to work this out, they established in 1987 this whole Earth telescope. And what they did is they basically had a whole series of telescopes spanning the full perimeter of the Earth. So what they could do is, when one telescope was observing the variations of one particular white dwarf and the sun was rising, then another telescope could pick it up, could take over. And this way they were able to do 24-hour, 48-hour or longer continuous observations of white dwarfs and work out their very precise fluctuations. And that allowed them to see that these fluctuations were indeed extremely complex, rather than just going in and out. These pictures give you a bit of an idea of the kind of, when the red goes out, the blue goes in. So it's almost like a throbbing. And you can even have situations where you have got different oscillations going on in the same star. And we can use that basically to look inside the star. The same way that we can use seismology to look inside our Earth, we can do the same with stars, and it's called astroseismology. And we can use that even in white dwarfs to work out various things, such as the strong magnetic fields, the size and composition of the core, temperatures, all this kind of stuff. So very, very interesting stuff. Now, and then finally, I wanted to finish with this. And this is M4 globular cluster. And by having such an abundance of observations of white dwarfs, we now have also been able to look at white dwarfs inside M4. And by putting these white dwarfs in M form on a HR diagram and looking at, say, white dwarfs in the galactic disk and put them on the HR diagram, we have noticed something really interesting. And that is this, the so-called luminosity abundance function. And basically what you would expect is that, more and more white dwarfs will appear, because more and more stars will become white dwarfs. However, they cool down. So you will find more white dwarfs that are less luminous than white dwarfs that are very luminous. Or basically, you'll find few hot and more colder white dwarfs. It's logical, because you get more and more white dwarfs, and you get a buildup of cooler and cooler and cooler white dwarfs. But there is a cutoff. There comes a point where beyond it, there are no more white dwarfs. And that tells us something. It tells us about when that particular part of our universe was created. Because if you have, a star turning into a white dwarf, if that star wasn't there, it wouldn't have turned into a white dwarf. So in other words, is we can measure the age of a particular part of our galaxy by looking at the abundance of white dwarfs and where that cutoff point is. Quite similar to in which you can actually see by looking at a HR diagram where the stars are bending off the main sequence. But this is very precise. In fact, it is a really great way of corroborating the information that we have from other ways of measuring the age of certain things. And here's the thing. By doing this, we can use white dwarfs to work out that the disk of our galaxy is in the order of 8 to 9 billion years old, whereas M4, the globular cluster, is near 13 billion years old, almost as old as the universe itself. So there is a huge age difference between the globular cluster M4 and the disk of our galaxy. And that is obviously extremely interesting, because clearly those globular clusters were there before the disk of our galaxy even formed. And it will help us to understand the formation of our galaxy and the world around us. Now, finally, then, of course, I said that was the last subject, but I have one more, this one. And that is obviously, can I see a white dwarf? And the answer is yes. And the easiest one for us to observe is not Sirius B, I'm afraid, because that is really difficult. Sirius is so bright, and whilst Sirius B is quite far away at the moment from Sirius, it will not be easy. And perhaps somebody like Rona with some Sirius double star splitting capability may be able to do this. But the easy one is this one, which is, as I said, 40 Eridani B. And to find it, I made a little finder chart here. Here is Orion. So we need to look at the time when Orion is nice and high in the sky. You take the bottom two stars of Orion. We are needing to go and find this star there. So what we do is we go one length, half a length, and then a little bit down the way. And that is when you find these two stars here. And that is 40 Eridani is this one, the bottom of the two stars here. That is quite easy to find. I've done it myself. But then you need a little bit of magnification, because the separation between the two stars, the two main stars, or the little group of the white dwarf and the red dwarf from K8, which is the main star, in this little group, it's about 83 arc seconds. So binoculars will be pushing it, I think. But certainly a small telescope with a bit of magnification will do. The stars are not dim. This white dwarf is about magnitude 9, so that is well within the reach of even a small telescope. But you need a little bit of resolving power. You need a little bit of magnification. Whether you will see the red dwarf, I doubt it somehow. That is quite a little bit dimmer. But those two stars you should definitely be able to split, and then you see a white dwarf, and that is probably the easiest white dwarf for you to observe. The reason why it took so long for us to actually discover so many white dwarfs, despite the fact that they are the most abundant object in our galaxy, is of course because they are so dim, and we can only see the ones that are really close to us. Now this one is not very far away, and as a result we can see it even with amateur telescopes. So I hope you enjoyed that talk, and if you have any questions, I'm more than happy to see whether I can answer those.
Well, thank you very much, Maarten. That was excellent, as expected. There's lots of questions. The first one from Eric is, can you observe the core young white dwarf in M57 I know you can image it, but can you actually see it with a scope?
I doubt it. I think, I don't know, Rona, if you can remember, but I think you're talking about magnitude 17 in the order. That
Yes,
is
I think so.
really pushing it for visual observation. Perhaps at the push, maybe with the telescope in our observatory, I would say do the calculation, run it through a calculator, see if you can see it. But I somehow doubt it. I can just about image it with my 6-inch Newton telescope and a video camera on it, and I think I can push it to almost magnitude 18. So it's the very edge, yeah.
Right, now this is a question from John McNichol. Do tidal forces between Sirius A and B cause visible changes in their spectra?
Oh, that's a good question. To be fair, I don't know. What we do know is that you can clearly see the redshift of Sirius B, and that has been shown. And in fact, it was one of the very first white dwarfs where redshift was observed. Whether or not it is possible to see the tidal effects between the two stars, I don't know. Is the short answer. I will have to look that up. There is a point where the stars are in line with each other. They do occult each other the way that it is, and you could see that in that graph. The two orbits cross each other. So there is a point where they are actually in front of each other, and that could potentially create an observable event that could provide us with some interesting data. But don't know about the tidal forces. So sorry, John, I don't know the answer.
David Ray asks, what are the sources of heat, and do the proportions change over the life of a white dwarf?
So the sources of heat is just basically what was left after the star died. So it's basically when the fusion reaction stopped, the core was tens of millions degrees. In fact, actually, when you are talking about helium flash, that would have heated up the core even more so. But a lot of that energy would have dissipated in the form of that flash. So you're left with just basically a hot ember, and it is not generating any further heat. It is just very slowly cooling. The thing though is because it's so small, a white dwarf, there's not much of a surface for the heat, for the radiation to escape, and that is why they remain hot for so long. In fact, actually, theoretically, white dwarfs eventually will cool so much that they become black. They eventually will be the same temperature as the universe, but we are talking tens of trillions of years, way long beyond after our sun is gone, and possibly even, by the end of the universe, basically, when some of these white dwarfs eventually will have run out of oomph. Yeah.
Oh, there was a question about brown dwarfs. So we're going to have white dwarfs, brown dwarfs, red dwarfs. Will there be purple dwarfs soon? But anyway, there we are. Can you actually observe a helium flash, or is it just theoretical?
No, you definitely can. Can you? What you can see is the effects on the outer layers of the star. So the star will expand quite quickly, and it will become brighter for a short period of time, and you can certainly see that. So when you're talking about young red giant stars in the early stage, if they suddenly flare up somewhat, then that is a clear sign that a helium flash happened. So I think the answer is you can observe it, but not directly, obviously. You will see the effects on the outer layers of the star.
Now, this is actually an unfair question because it's not really relevant, but I've been asked by two people, what do you think of the peculiar behavior of the recent Cassiopeia nova? I know it's not a supernova, but you know how it was going up and down.
Yeah, but let's have a very, very brief matter about novae, because I didn't mention them, but almost all what we call cataclysmic variables and things like novae are nearly all created by white dwarf stars. So, for example, a recurrent nova or any nova is very often created where gas lands on top of a white dwarf which is still extremely hot. And what can happen is if enough hydrogen from a nearby star is absorbed by that white dwarf, instead of the white dwarf going supernova, it can just become so hot underneath that shell, that underneath that envelope of hydrogen gas, that the hydrogen just fuses, and because it's so close on the surface that it will just basically flash away, and the star brightens not as bright, nowhere near as bright as a supernova, but we call that a nova. So yeah, novae are nearly always caused also by interactions between white dwarfs and companion stars. So it's a good question. Novae. Yeah, very much related to.
The only difference between a supernova and a nova is that there's nothing left after a supernova, whereas a nova can be recurrent.
Absolutely, and I suppose it depends on which supernova. A type 2 supernova, where you have a core collapse inside a very massive star, you will have something. You will have either a neutron star or a black hole left over. But the type 1a supernova, when a white dwarf goes supernova, smithereens, nothing left. Yeah, an expanding shell of gas, and you should be able to observe that for quite a while until it becomes so dispersed that you cannot see it anymore. And yeah.
Well, thank you very much, Maarten. That was very interesting. Thank you.
It's a pleasure.
Well, Rona, thank you very much for handling the question and answer session tonight. There were some fascinating questions submitted tonight, and I know you had your work cut out to select just a few of them for Maarten. And Maarten, can I just take this opportunity to thank you for a most interesting, captivating and enthusiastic talk, as usual, I might add. Pre-COVID times, you'd be here with us, receiving thunderous applause and a token of our appreciation and a thank you card designed and printed by Pauline. But we'll need to send them to you via Pony Express just now. You should always know there's always a space for you as a member in our club, Maarten, and you'd be made very welcome. Anyway, Maarten, thank you very much once again, and I hope you can stay with us and experience the rest of our club meeting.
Well, I certainly will. Thank you very much, Eric. It's a pleasure.
Thank you. And now for something completely different, Chatz. We're very aware that we haven't been getting the chance to meet up in person, so we've decided to try something new. We're bringing ourselves to you and letting you know a wee bit about ourselves, what we do, and what we've been getting up to from an astronomy point of view. So here's a 10-minute recording from an interview I did recently with Lisa Pattenden and Matt Lafferty during peak noctilucent cloud season. Thanks for joining us today, Matt and Lisa. You know the situation behind us having a little club get together. We're having a little members moment session, and I'm just glad that you two have volunteered to come along and talk to us about the astro experiences this month. Now, many people in the club won't know you guys. They'll have heard of you because they know that you're part of the Tech team, the main people that keep the show on the road. So we have Lisa Pattenden, and I'm sure folk have already recognised that Lisa's accent gives away that she is not native from the island. Lisa, where are you originally from?
I'm originally from Washington, D.C., but I've been in the country 13 years now, so
You're
dual citizen. My heart is here.
You're almost a native.
Yeah.
Yeah.
Minus the accent.
Don't ever lose the accent.
I will.
Yeah. And Matt, you're definitely a local lad, I think.
Yeah, born, raised in Inverness. I did spend 12 years in Glasgow, but I'm glad to be home. So you might hear a little Glasgow in my accent, but I'm trying desperately to get rid of it.
No, that's always flattering to the people that you've spent a long time with. So.
True, yeah.
Now, both of you guys are very, very active, practical astronomers. What got you into it?
Oh, well, my father was a sailor, so when I was a kid, he used to point out all of the constellations to me. And like one time as a gift, he was able to get me into the National Observatory in DC, which is right next door to the vice president's home. And I saw Saturn for the first time, and that was it. I was done.
That's
It was,
the wow effect, isn't it?
oh, I was like, oh,
Yeah.
Dad, it's not just the movies. You know?
It's wonderful. The first time you see Saturn and the rings around it, it's just wonderful. Jupiter's another one like that.
Yeah,
Actually.
yeah.
You see the bands or the red spot or the moons, you know, the Galilean moons round about it. They're
Absolutely.
fantastic wow factor. What about yourself, Matt?
I don't think I can pinpoint it really. As long as I can remember, I've been fascinated by just the night sky and the stars and everything behind it. Yeah, so quite early on, I started asking for books for birthdays and Christmases and reading up on the stars and the constellations and just staring at them endlessly. The one thing I do remember is probably from about age 10, I spotted the Pleiades, the cluster, and something about that just fixated me. And I've spent basically the rest of my life, the first thing I do when I look up at the sky is look for that. And I just stare at it for a while. Yeah. And then I got a pair of binoculars for my birthday a few years ago. And the first thing I did with those was look for the Pleiades. And I looked up and I was just absolutely blown away. Because it's 7 stars. And then you put a pair of binoculars to your face and look through again, and it just explodes. And there's innumerable stars just right in that little tiny piece of sky.
I think it's one of the best binocular objects, Matt.
Yeah, oh, absolutely. I agree.
There's another member in our club, Fritzie Folds, and she mentioned to me one time that she thinks it looks like an octopus. And once I saw what she meant by that, I can't unsee it. I've never seen it in any books, textbooks, or astro magazines described as an octopus. But you have a look at that when the sky's darkening again and just see if you can see it. It makes it fun.
Yeah,
makes it fun.
I've can't even picture it in my head. I can't see that, but I'll definitely look for it. And probably that's what I'll see it as from now on.
What we're really here about tonight is you observe with cameras.
Yes.
Now, all of us had a fantastic observing experience just a few days ago.
Yeah.
When we were alerted to the wonderful noctilucent or night shining clouds in our skies at this time of year. So how were we alerted, Lisa?
I was looking out the window before I went to sleep and got on WhatsApp and said, NLC's in the house because they were there. I could just see them barely starting. And I don't know what it is. I feel like there's this calling. If the northern lights come, I get this calling. If the noctilucent clouds are there, I get, and it's just something compels me to keep my eye on the sky. And there they just slowly just started to appear, and it was quite a great show we had till the big cloud that you sent my way, Eric, came.
Oh yeah. Now, for those of you who don't know, the club members, we have 2 WhatsApp groups. One is called Cosmic Convos, and that's for general astronomical discussion or even general social discussion. But we also have a group called Nebulous News, and we use that as our alert system. So when one of our members sees something, observes something, or wants to ask a question of someone, they just get on there anytime of day or night, and it gets a whole group of people out the back door looking up at the sky. And that's the whole point of it. And it worked absolutely superbly for this particular event. Now we got quite a few pictures, which we're just going to show a couple of these, and we're all going to probably talk our way through them. Right, Lisa, this after the alert, you started to ping pictures up onto WhatsApp.
Yeah, this one actually is from the first time that I noticed them, June 5th. I was just in awe because it is a lot like the Northern Lights, however, a lot trickier to photograph. So I was messing around with the ISOs. I was moving around the f-stop. I was just like, how can I get what I see onto this camera? And then I finally got it. So this window is the only window out that the north of my house. So it is my go-to landscape when people see my photos.
Yeah, but I
'cause
think that's important, Lisa, is you don't actually have to get in your car and go
exactly,
anywhere.
exactly.
Um,
I'm in awe of the fact that it's so vibrant looking when you see them, and there's you could see to the left, the far left in the corner, there's even a bit that's kind of cloaking around that house, so it's kind of like it's bouncing off the roof of the
I see that.
house,
Right, nice.
But I mean, they really gloriously changed, like over to the right above that tree, that bit started growing into something as well, and just a really neat experience. I was just like, okay, I like the NLCs now.
And now,
Ta-da!
here is a photograph obviously taken by an expert NLC photographer. Matt, would you like to talk us through this one?
Yeah, so this is actually, I'd never even heard of Noctilus and Clouds until I was chatting with you guys, and we were coming up to Noctilus and Cloud season, and everyone was talking about it, and like, oh, the season's coming up, and I was just sitting quietly. I don't know what this is, but would it be a stupid question? And then finally somebody explained what it was, and I got really, really excited. Having never knowingly, I've probably seen them in the past, but never realized what I was looking at. Yeah, so I've been waiting quietly, glancing at the window at about midnight every night, waiting for it to happen. And of course, the one night that it does happen, I was tucked up in bed by 11:30. And thankfully, I forgot to put my phone on silent, so I got that alert that Lisa sent through and immediately jumped out of bed and ran to the window. And I took a few photos. So this is probably, I think this was taken about midnight by the time that one was taken. And each photo, they got progressively more just stunning. And this is, I've tweaked it a little bit just to change the contrast and things like that and really bring out what I was seeing, because with photos, I find you never capture what you're looking at. It doesn't look quite the same in a photo as you do with your eye, and that always frustrates me. So I've done what I could to make it look how I was seeing it. But I can't tell you what my aperture was or what my shutter speed was, because I just used this thing, and it does it all itself.
Yeah,
It's a superb
it's well
picture,
done.
honestly.
Thank you. This is the first time I've seen them. It's the first time I've photographed them, and I think using just a basic camera phone, it really shows what can be done.
How accessible it
Oh,
is.
yeah, there you go. There's our accessibility thing again.
As much as I'd love to have a go with somebody's big fancy telescope and lovely digital camera setup and all that stuff, it's nice to know that you can just nip outside and grab a photo.
And if you don't have a phone or a camera, don't worry about it. Go out and just look at them with your naked eye.
Enjoy
There's an emotion, there's an atmosphere about them. It's best, yeah. Well, that is our first experience at doing a Chatz interview, and I hope you enjoyed that as much as we did recording it. Anyway, over to one of my favourite parts of the monthly meeting. We're going to the club news and Astropics from the month, and Pauline is back with us again, and she's going to show you what our club and other amateur astronomers and observers in the north have been getting up to. There is an abundance of photographs taken by us over the past couple of months, so to give her the time the section deserves, straight over to you, Pauline.
Okay, thank you very much, Eric. Okay, I'm first going to offer an apology because I've only just found out that my mouse makes a terrific clattering noise during my presentations whenever I'm moving the pointer around. I've now got a mouse mat, so I'm hoping that everything is going to be a lot quieter. So we're going to start off with the club news and a plea that we are still looking for a secretary. We're not going to have Rona for very much longer, but if you feel that that's a little bit too much for you, then we would be delighted if we could just have you as a committee member. It's always nice to have new blood, new views. So get in touch with us. We don't bite. Now, the observatory has had its biosystem, or the pure flow system, serviced at long last. And this is what it's all about. So there's a peat layer underneath this bit here. And the peat filters the effluent, which is pumped by this pump here. And the effluent, of course, comes from the septic tank, which is over here. Now, the septic tank isn't actually part of the biosystem itself. We're very fortunate that Tom was able to say that everything looks absolutely fine. The peat will probably need changing in a couple of years, and at that time we can also get the septic tank pumped out. And the really nice thing is that we were only charged £100 and not 200 as it should have been. We have a risk assessment in place up at the observatory to make it as COVID secure as possible, because we want to have our first observing session this month. And so a few of us went up to the observatory to have a look and decide what kind of risk assessment, or to decide on the risk assessment. So we've got a little video here. There's Dave and me. There's Matt, Jerry, Anthony, Andy, Rona, and of course our esteemed chairman, Eric. And Jerry is our observatory manager. Here we go. Now, we were absolutely delighted to receive a check from Arthur's estate of £1,000. And this was just an absolutely wonderful thing for Arthur to do. So it's now safely tucked into our bank account. There are still a few of Arthur's books left. I'll send out an updated list with Stargazy Pie. I hope you'll choose one. Think of it as a gift from Arthur. Still haven't got round to organising the auction yet. That's something that will be done. And those of you who have asked for particular books, not all of you will have got them yet, but that is something that's also being organised at the moment. I can't believe we've got to August already. New moon on the 8th, the Perseids, which we hope to watch this year at the observatory. The peak is the 12th to 13th. Astronomical darkness begins the 14th of August. So this is true darkness, and we get about 3/4 of an hour of it on the 14th. But that will extend as we go up to the winter solstice. And then we have the full moon on the 22nd. Don't forget to look out for the summer triangle, and we've got Jupiter and Saturn. Now, the Perseids is a really good meteor shower to watch, particularly so this year because there is no moon that would normally spoil it. The radiant is the area from which the meteors seem to radiate. And if you want to find it, if you look for Cassiopeia, which at around 1 o'clock in the morning, a little bit before and after that, of course, it is on its side. And what you do is just to look at the lower part of Cassiopeia and you will find the radiant. If you're still not sure, you can move down and to the right-hand side and you'll get to the Pleiades. And Pleiades marks the end of Perseus's foot. And also you can look for the end of Cassiopeia, go all the way down to find a bright star. That's Capella. So that is where your radiant is. They always suggest don't look exactly at the radiant. You'll actually see more meteors if you look around the edges of it. And it's named, of course, because the radiant is close to Perseus. It's active between the 16th of July and the 23rd of August, which means that if you looked out towards Perseus at the moment, you would see a few more meteors than you would normal nights. The peak itself is the night of the 12th and 13th of August, when there can be up to 50 to 70 meteors an hour. That's 1 a minute, which is quite extraordinary, quite a lot. Many of the meteors have bright trails. And the best time, of course, is when the sky is at its darkest, which for us will be around 11 o'clock. There are not just peak nights, but peak times. And this time it's thought to be between 8 and 11, although there are some schools of thought that say that it could be around 3 a.m., although I will not be up at 3 a.m. And the shower is due to the comet Swift-Tuttle. And it has a particular orbit around the sun every 130 years or so. But as it moves around in this orbit, it leaves behind a trail of dust. The Earth plows through that dust in August every year, and that is what gives rise to the meteor shower. So we're going to meet up at the observatory on Friday, the 13th of August. Now, I know that is the night after the peak, but there will still be a lot of meteors, and we've made it Friday because then that's easier for all of those who are at work. What we need to do is to ask you all to write your name and telephone number on the paper provided. This will be for track and trace purposes. We recommend wearing a face covering when inside any of our facilities, although we're going to really limit anyone going in at all. But of course, you are allowed to use the toilet. And of course, if you are in close proximity to anybody, then it's polite just to put on your mask. We've provided wipes so you can clean any surfaces that you touch, including the toilet. Now, I did go up to the observatory yesterday and gave the toilet a good cleaning, and I vacuum cleaned the observatory too. The floor needs a good wash, but I don't think you'll be on the floor, so we'll be all right for a little bit longer. Now, don't forget, although we're going to be up there at 9:30 when it's still light and could be fairly mild, it will get cold, so you must dress warmly. Bring your own tea, coffee, food, because we will not be providing tea and coffee. As I said, we're going to limit anyone going into the observing station at the moment. Bring deck chairs or a blanket to lie on. Deck chairs are great because you can sit them right back and then you can just look straight up in the sky. Now, all you need for equipment are your eyes and deck chair or blanket. But it's quite nice to be able to photograph the meteors. And if you're not sure what you're doing, then there will be tuition or coaching from some of our experienced members. And the other good thing about arriving at 9:30 in the light is that you can then set up your equipment. You can work out the best place to put your deck chair. Finally, please do not attend if you're feeling unwell in any way, even if it's just a headache or a sore throat, or if you're feeling particularly tired, because these can be symptoms of COVID. If the weather is unsuitable for meteor watching, then we can have a social get together and a general chat. But if it's pouring with rain, don't come. And if we have to cancel for any reason, you will be notified by email or by WhatsApp. Now, if we do get a clear sky and we're able to see the Perseids, then you will also be able to see Jupiter and Saturn. They're fairly low down in the southern sky, whereas of course the meteors are going to be more visible in the northeastern sky. Jupiter is lovely and bright at the moment, and Saturn a bit dimmer, but it looks yellowish, really quite yellowish. Both of them are coming up for, well, Jupiter's coming up for opposition on the 19th, and Saturn was at opposition yesterday, so last night. An opposition occurs when the Earth lies exactly between the Sun and the outer planet. It means that it's directly south at midnight, that's GMT, and that means it's visible all night. But because it's still quite low in the south, don't forget to give it a little bit of time to rise, and also, of course, for it to get a bit darker. Opposition is always a good time to view the planets because of their position in the sky. But notice that Saturn's rings are actually on the verge of closing at the moment. And in 4 years' time, they will be edge on. And this is the reason why Venus is so difficult to see at the moment. It's very low down in the western sky. As we move into November and December, it will rise that little bit higher. Darker evenings, you should be able to glimpse it at sunset, hopefully, if you've got a clear horizon at that point. And then it'll start gradually disappearing once again. So now we come on to the photographs. And not only are they brilliant as always, but the really good thing is that we have got more people contributing to the photographs this time. So this is Stephen Charlton of North Ronaldsay, and we've got Jupiter here with the 4 Galilean moons. We've got 2 each side. Now note the date, this is the 17th June. And then Mick took this photograph of Jupiter on the 22nd. And although we've still got 2 moons each side, they've actually all swapped positions. On the 1st of July, you can see that 1 moon is quite far out. This is actually Ganymede. So it's gone from this side to the previous side, to the other side in the previous photograph, and back to this side. And then 4 days later, Dave has photographed Jupiter, and you've got the bands on Jupiter absolutely beautifully. But now we've got Ganymede still on this side by itself because we've now got 3 moons on this side. So it's always worth watching the moons of Jupiter. You only need binoculars if you've got a dark sky sight, although a telescope will show them a bit better. And you can see how they change, how they move night by night. Here we have Jupiter and Saturn by Mick. And this was the 1st of July. And here we have Saturn and Jupiter. So the image has been reversed this time, but you've got the 4 moons here and you've got the elongated shape of Saturn. We've got a number of solar photographs which are just extraordinarily beautiful. This is by Eric with this wonderful prominence here. And Neil from Aberdeen has also photographed this a prominence, but you can see it in a loop. Can you see that? And this is a nice big sunspot known as 2833. And the same sunspot was captured 2 days later by Eric. And you see that with hydrogen alpha, you get this very reddish orangey tinge. With hydrogen alpha light, we are looking above the surface. We're looking at the lower part of the atmosphere, known as the chromosphere. And Eric has also captured this wonderful, quite pointy prominence here. Now, this is a white light image. So we're looking at the surface of the sun, or the photosphere. And these are sunspots, 2835. It's given to the 2 of them. And these are actually a pair of sunspots. And this is another set of sunspots here, 2836. So just bear this in mind. Look at the little semicircle here, because you'll see that time and again. Now, the same day, Eric photographed the sunspots that Dave had photographed. And this is in hydrogen alpha light now. And if you look carefully, you can see that both sunspots are almost joined by this white area known as a plage. which is to do with magnetic fields, because very often sunspots come in pairs and they are joined magnetically. Now we can look at them in close-up, and this is just a fabulous picture by Neil from Aberdeen. And you can see the big sunspot here, but notice the other sunspot has actually decreased in size. So that's just 2 days later. Excuse me. And there is that semicircle in between them. And that was that other smaller set of spots, but we're not seeing all of them at the moment. And then a day later, on the 1st of July, this is an image by Andy Broch, and he was delighted because this was his first ever photograph using a quark hydrogen alpha filter. Now this is where you take out the diagonal, you put in the quark filter, and then you put the eyepiece on top of that, or into the quark filter. So you are filtering the bit where you look in, instead of filtering the end of your telescope. So this isn't a dedicated hydrogen alpha telescope. This is a special filter that you put into where you would normally look in with the eyepiece. So that's the difference. And I'm assuming, because the photographs are similar, that perhaps our previous photograph with Neil Weston may too use a quark filter. Slightly different orientation. So now we've got the big sunspot, the little sunspot, and you can see very clearly how the magnetic field lines extend between these sunspots. So it's the magnetic field entraining all the plasma, and it's just extraordinary. So if we go back a day, we've got Neil using white light to photograph the sunspots. And once again, you can see how small this sunspot has become. There's your semicircular bit. And there is the other set of sunspots. We've got 2 that you can see. But the day after, again, it's a white light image. Dave has photographed the sunspots, but we've only got 1 here now. So this again shows you how quickly the sunspots can change, which is why it's worth looking at them every day. Again, it's a different orientation, but there is your semicircle, and that's your second spot, which is just shrinking all the time. So this is the whole disk that Eric has taken, again, hydrogen alpha. You can see the big sunspot quite clearly. That's your semicircle, and that's the smaller one. Very difficult to see the little sunspots. And here is another sunspot over here, which I forgot to point out in Neil's image here. And again, it's just different orientations. And this one wasn't associated with anyone, this image, but I'm pretty sure it's by Neil in Aberdeen. And this is a filament, which is an area of gas that is suspended above the surface, but it's within the chromosphere, so it's within the lower atmosphere. And you can see it rising up, going down and rising up again. And the reason it's dark is because it's slightly cooler than the area around it. If this filament was on the edge of the sun, we would call it a prominence. This is a beautiful photograph. In fact, the 2 of these are, this is the sun taken at the summer solstice. That sunspot is so big that you can see it quite easily on the sun. And here we have the sun completely setting. Now, Dave has had his own solar project on the go, where he's projecting the image of the sun. And you can see that quite clearly. So this is something that you can do. If you don't have a telescope, you can try doing it with binoculars. It won't be quite as big as this, but you can see enough detail to be able to pick out the sunspots, particularly if they're large. There are a few artifacts here, but there are 2 definite sunspots, which you can see here. And of course, there are always phenomena associated with the sun. So Michelle from Sigma has photographed this absolutely wonderful sundog, which is caused by refraction of light through ice crystals. It occurs on usually, sometimes both sides, which should occur on both sides of the sun. We can see it quite clearly on this side of the sun. And when Michelle moves over a little bit, you can see that there is a second sundog, but it's a lot fainter. And Pete from Sigma was obviously out on the same evening. There's the sundog reflected in the water quite nicely. He's covered up the sun, although you can see its reflection. But look, you've got the sundog the other side, just as Michelle saw, but it's much fainter. And this sundog, beautifully bright, imaged within the water. And then Neil has photographed this sun halo, a complete ring around the sun. It occurs when you've got cirrus cloud, which you can see all around here. Again, refracting light through ice crystals. And that's what's giving you the ring. And then we had a bit of excitement with a partial solar eclipse. So this is Lisa's setup. You can see that it was quite cloudy for a while. She uses her camera, and I'm assuming this is a telephoto lens. And she's very sensibly wearing eclipse glasses so that she can spot the sun, but keep her eyes safe. And this is her photograph of the eclipsed sun. It's beautiful, absolutely beautiful, but you can see there's quite a bit of cloud around. This was my attempt. I've had to enlarge the photograph so that you can see where the sun is. And this was with my mobile camera, and I simply held it up to the sky and photographed it with a hoping for some luck that I actually managed to capture it. But it's not perhaps something you should be doing if you don't wear any eye protection. However, I do have a telescope with an ETX 125 with a solar filter, a white light filter, and I managed to get these two photographs. So this was when it was quite cloudy, and then it cleared and was magnificent. Now, while it was cloudy for us in Inverness, it was incredibly clear for Eric, who did a live solar session. And the eclipse that he caught with his telescope on camera was just wonderful. And then when the sun came out in Inverness, I think it got cloudy with him. But if you look carefully, you can see all the lumps and bumps, which are due to the craters of the moon. But this is a particularly spectacular photograph by Dave, a close-up, which shows the lumps and bumps, all the craters, all the up areas and the down areas on the moon, absolutely beautifully. You forget it's the moon that's passing in front of the sun until you see a photograph like this. And now we have our noctilucent cloud gallery. There are quite a few of these, so I will go fairly quickly. Now, I thought that Dave and I were the first to see the clouds and photograph them. This was the 15th of June. But from what Lisa was saying in that video, she obviously spotted them before we did. A few days later, Eric took these. Day after that, Lisa saw more noctilucent clouds. Absolutely stunning. And Mick also Mick from Sigma also photographed the noctilucent clouds that night. What I find astonishing is we've got these wonderful filaments, and then look at these horizontal bars that you have within or maybe just behind the cloud. And you can see them again here. And this is particularly bright strands. This is where you get this very bright silvery color of the clouds. And we have a few from Alan Tuff of Sigma, which are just extraordinary. Now, if you note the time, this says 10:30 universal time. So that's GMT. So we need to go forward an hour. So this would be 11:30 GMT. And then this will be midnight. There are those horizontal bars again. And this is the same night. And this is 12:30, 1:45. And very often around 1 o'clock seems to be a very good time to see noctilucent clouds. This photograph appeared on the front page of Space Weather. And this was around 2 o'clock in the morning. Look at these incredibly bright filaments. They're just beautiful. And this is a close-up. And here's Matt's photograph again, same night, beautifully done. And Andy Brough, one of our treasurer, took this incredible photograph. Mick O'Donnell of Sigma, and this is all the same night. And I was really annoyed because all I kept hearing were these pings coming through on the WhatsApp phone saying, oh yes, more noctilucent clouds, keep looking outside. And I was in Gloucestershire where it was cloudy every day and every night for virtually the entire fortnight. I was down with my father. But again, you've got this horizontal banding with these vertical shafts of cloud. And Dave has also captured this horizontal banding. It's quite extraordinary. And I love this one. You see this really bright filament? I bet that was around 2 o'clock in the morning, same as Alan's photographs. This is more noctilucence by Pete from Sigma. So we're looking at Elgin. Every time you see Sigma, of course, you think of Elgin area. And we've got those bright filaments again. And Neil in Aberdeen. So we're now right over on the eastern side of the country. So it just shows how far the clouds extended without too much cloud in the way. And Lisa, once again. And Sharon Sutherland from, I'm pretty sure you must be Inverness, Culloden Way. Absolutely stunning images. And what I love about this time of night is this perpetual sunset to sunrise all the way along the northern horizon. So Eric, I wonder if this was around 2 o'clock in the morning because we've got this really bright filament. Here we go. That must be 2 o'clock. And of course, noctilucents are our highest clouds formed in the mesosphere, 80 to 85 kilometers high. They're formed of tiny ice crystals which surround even tinier dust particles from meteors. And this is from Eric's all-sky camera. So this is about 12:30. You can see a lot of cloud and it clears. And then you've got this wonderful set of noctilucent clouds. And this is 1 o'clock in the morning, always a good time to see them. And then they appear very slightly to disappear. So we get a dark area and then they come back. So around 2 o'clock, we get these really bright filaments. And that's what we've been seeing in the photographs. And then it's dawn. And this is 2:30 in the morning. It's just extraordinarily amazing how quickly dawn comes. And then 12th of July, there were a series of noctilucent clouds. So that was Michelle from Sigma. This is Alan again from Sigma the day after. Lisa on the 13th. We had more cloud, obviously. And Fiona Macrae from Stornoway Astronomical Society. She's not part of the SAS, but she must have been in Aberdeen on holiday and managed to photograph these stunning images. The day after that, yet more noctilucent. So it's been an incredible time. We have had a lot of ha here in Inverness, and I think that has unfortunately spoiled a number of evenings when we might have been able to see noctilucence. So this is now the 15th. We're nearing the end of the noctilucent season. The latest I've seen them is the 7th of August. So we've only got a few more days to go before we lose them until next year. And another one from Lisa. And again from Dave. And incredible photographs from Alan in Sigma. You obviously had better skies than we did. And now I've got 3 of the moon. We have this wonderful crescent by Mick. And he's, after what I've been saying about how difficult it is to capture Venus, there we go. We have an unknown contributor here. Is this from you, Pete? There is the first quarter moon. And this wonderful, just past full moon rising from the Ha by Dave. And interestingly, Dave has photographed the Nova in Cassiopeia, which is still going strong. So we first saw it in March and it's now July. We're finishing with this one from Rona. Beautiful shafts of sunlight coming through the clouds into this glorious mountainous scene, which is presumably normally covered in snow. So thank you very much, everyone.
Well, Pauline, thank you so much for that again. That was, as usual, a perfect balance of club news, practical astronomy for us astronomers, and absolutely wonderful images. Well, that is just about us for tonight. I want to thank our technical support people, well, which is basically Matt, for working so hard in the background prior to the meeting and also tonight. The night might be finished for most of us, but if you do want to join us for a wee informal blether, if you click on the link which is in the chat box, you might have to scroll back a little bit to get it. I found out that it wasn't in any of our emails that we sent to you, so you'll need to use the link in the chat box. Oh, I think it's been sent out to everybody again. So if you just click on it, once you've clicked on it, you'll see a screen or a box telling you the meeting is yet to start. It'll just take Matt a couple of minutes to shut down this meeting and open up the chat room. So just hang about a wee while until he does. To all of you, thank you once again for coming along. Until the next time, clear skies and keep looking up.